Okay, now we are going to discuss points of inflection. So I took our previous example from concavity. We had x squared plus 1 over x squared minus 4, derivative, second derivative, intervals, concave up, concave down, concave up. Okay, we got the intervals based on points of non-differentiability. So let's look at the definition of a point of inflection. Let f be a function that is continuous. Again, that's kind of like a recurring theme here on the open interval. And let c be some point in that interval. If the graph of the function, graph of f, has a tangent line at that point, where x equals c, if there's a tangent line there, then this is a point of inflection of the graph of f. If the concavity changes, from upward to downward, or vice versa, downward to upward. So, a couple key things there. The function must have a tangent line. So let's look at this example here. We have concavity changing from up to down, down to up. So it stands to reason that negative 2 is x equals negative 2, a point of inflection. Well, let's read this. We have a continuous function on an open interval. Okay, well, this actually is not continuous. At x equals plus and minus 2. So, we do have a continuous function from negative 2 to 2. Open interval negative 2 to 2 is continuous. Within there, there's no changes in concavity. Okay, so right away it fails the first test. Secondly, okay, if it was continuous, let's hypothetically say it was continuous on the interval from negative infinity to infinity, the fact that negative 2 came from a point of non-differentiability means there's no tangent line there, so this could not have been a point of inflection. All right, so just because concavity changes does not imply a point of inflection. The concavity needs to change, and it had to come from a point of differentiability. So let's look at this next example down below here. F of x equals x to the fourth minus 4x cubed. First derivative, second derivative. So let's just find the concavity so we know if it changes or not. Set this equal to 0. Factor out a 12x. I get x minus 2. So I get two critical numbers, 0 and 2. So negative infinity to 0, 0 to 2, and 2 to infinity. So let's test this. Let's take a negative 5, for instance. Well, that makes a negative, and a negative makes a positive that is concave up. 1, positive and negative makes a negative that is concave down. Let's take the value 5. Positive, positive makes a positive. This is concave up. So, right here, we have a change in concavity at x equals 0. And here we have a change in concavity at x equals 2. Both of them came from points of differentiability, right? They came from zeros of the derivative, critical numbers that were not points of non-differentiability. Therefore, x equals 0. 0 comma my y value is 0. And 2 comma, well, that's what, 16 minus 32, 2 comma negative 16 are points of inflection because the concavity changed and our function was continuous and tangent lines exist at x equals 0 and x equals 2. Points of inflection, look for the change in concavity and verify it came from a point that was a 0 of the derivative, not a point of non-differentiability. That's all I got for you, points of inflection.